In example 2, we want to determine our Norton equivalent as well as the voltage drop across our 2 kilo ohm resistor. To begin, we are given a 12 volt source that's connected in series with a 6 kilo ohm resistor. This non-ideal source is connected to a resistor with a value of 2 kilo ohms at terminals A and B. To begin, we will construct our Norton equivalent circuit. That is, we will have I sub P in a parallel configuration with R sub P connected to our 2 kilo ohm resistor at terminals A and B. We have to determine the magnitude of our current source as well as the value of our parallel resistor. To begin, we recall I sub P, or our short circuit current, is equal to V sub S per R sub S, where V sub S is our open circuit voltage per our Thevenin resistance, which would be 12 volts per 6 kilo ohms, or 2 milliamps. We recall R sub P is equal to R sub S, which is equal to our Thevenin resistance, which takes a value of 6 kilo ohms. To determine our current running through our 2 kilo ohm resistor, we will use current division, where we take our opposing resistance, R sub P, over the sum of R sub P and 2 kilo ohms times our source current, or 6 per 8 times 2 milliamps. Last but not least, to determine our voltage potential across our 2 kilo ohm resistor, we have to take the current running through said 2 kilo ohm resistor, i.e. 1.5 milliamps, times said resistance to give us 3 volts. To verify, we can look at our original Thevenin equivalent circuit and do voltage division. That is, our voltage potential across our 2 kilo ohm resistor is going to be our 2 kilo ohms per the sum of our resistances in series, 8 kilo ohms, times our source voltage. Therefore, our voltage drop across our 2 kilo ohm resistor is 3 volts, which matches our Norton equivalent circuit.